I'm Jelle.
And I'm Feli. And today we're going to talk about how to actually make an algorithm from scratch.
That's good. So I've learned that there's many algorithms. So what kind of algorithm are we making today?
So we're going to start with linear regression because we talked about a bit about linear regression before and about how it's an algorithm that's relatively easy to understand, to explain, to visualize. So I figured linear regression is a good place to start.
That's good. So how are we going to make our own algorithm? Do I have to, do I get to write some C# or...
No C# for you.
That's too bad.
So we're going to be making this in Python, and I'm using Jupyter to actually, use the code because it gives you a really easy way of also just displaying the sub-steps, so to say. And I'm using datasets from this site, Scikit-learn, and I'm now going to use the Boston house prices dataset. So that's a dataset which gives you the price as a label, and then it has 13 different predictors. Yeah, it has 13 different features that you can use.
Can you give me an example of one where you think, well, that's not going to work?
Yeah, we have a few that are, let's see. We have a few that gives you just an H or nitric oxides concentration, and there's a lot of them, and I think there's a lot that aren't going to work.
Good.
But we will also find out
which do work.
Which do.
That's good. I like that in my algorithms.
Yeah. So we're just starting by loading our Boston algorithm. Our Boston dataset. And we can see that it has the 13 features on it. So we're just going to use feature 5, which is the average amount of rooms that there are.
That sounds like a great way to predict how much a house costs.
Yes. So if we load that, we have to split it into a train set and a test set.
As we've explained before.
Yes, and we are only looking at the price and the amount of rooms. And here you can see that if we plot these values against each other, the average amount of rooms and the median value of the price, then we can see that it looks like it might be linear.
Which is
good.
Because we want that.
Yes. And you can see a couple of outliers, but it looks linear enough to give linear regression a try. So
outliers here would be houses with very few rooms for their price.
Yes. So here you have, you can clearly see all of the rooms are kind of clustered here, but there's a couple of rooms that are a lot more expensive that don't necessarily have more rooms, and you have one place that has, about 9 rooms, but it's not as expensive, it's almost half as expensive as other houses that seem similar in the amount of rooms that they got.
But still, because the amount of outliers is manageable, we can...
Yeah, we can still try. We can always try. So what we're doing is first we got to do a bit of math. So we calculate the covariance, the variance, and the mean. The mean is probably something that...
I would hope everyone here knows what the mean of something is.
Yeah, so the mean is basically just the average. And then we do the variance, which is how much something changes. Like,
how much values differ from that mean, basically,
Yeah.
right?
And then we have the covariance, which is also just a way to get a variance. And for this, the only thing that is important to know is that if points are more similar, it's higher. So and for this, again, you don't have to know the exact math. You just have to find a formula on the internet and program that.
But I think it would help if you have some basic understanding.
Yeah. It's good to know the basics, but there's a lot of videos, so you can just read a book about it. Spoiler, there are books. But once you know the variance and the covariance and the mean, we can calculate the coefficients. So every line, if you have a straight line, you can write it as ax plus b. So a times x plus b is I. So y. So what we're trying to find out is which values of a and b work best for this data set.
Right. So you want the line that that best reflects the data set's actual line, where the error of all the dots, like in a perfectly linear model, you'd have a line. You don't. You have dots around a line, but you want to find the line that best represents
this data set.
And for that, we use the formula y is ax plus b.
Yes, that's what we do. And you can see here is that we use the different means, the covariance and the variance, to calculate the slope and the intercept. So the slope is just how much the line goes up, and the intercept is basically the value that you would get if your x was 0.
So basically equal to the b of the formula.
So that's equal to the b of the formula, and the slope is equal to the a of the formula. So once we know how to calculate these, which we now kind of do, like we programmed it, so then we can already start plotting the dots that we saw before.
Yeah.
And now also plot our line through them. And you can see that the line kind of follows, like, it's decent. It kind of works. It's, it's a line.
It's telling us if your house has more rooms, then probably it's gonna be more expensive.
Yes. So then now that we have our slope and our intercept, the only thing that we need to do for the actual linear regression algorithm is for every data point in our test set, we need to check what the y value would be, so what the actual label would be. So we just do that by doing the test row times the slope plus the intercept.
So what we're calculating right now is we already know the actual value of each data point, and we're trying to get the predicted value that our model would say that dot has, right?
Yeah, like we are giving this algorithm, we are telling it what is the x value, so in this case the amount of rooms. Then for the train set, we're giving it the price for the train set, and we're giving it the amount of rooms for our test set. Mm-hmm. And now for every amount of rooms in our test set, we're going to check what is our predicted price.
Right.
If you actually apply this to a new house, then you wouldn't know the actual value.
Right, because if you knew the actual value, you don't need
Why
AI.
would you do this?
you just know.
Yeah, so after that, we can just see the actual value and the predicted value for a couple of examples. And you can see our first example the actual label and the predicted label are pretty close, but for some others, we're less close than, like the predicted label isn't always the same as the actual label, but they...
Which we could see in the graph,
yeah.
right? So the line hit some dots, but it also really missed some
Yeah.
dots.
Yeah, because you can see, this dot was absolutely hit, this dot was hit, but the rest, it isn't perfect, but it kind of works.
Mm-hmm. On average, it tells us a good estimation.
Yes. Yeah. So, we have a predicted label, we have an actual label, but this gives us per test row, we now know how it performs.
But I would like to know how my entire model works, right? So
Yes.
I don't want to know how well did I predict the house with 9 rooms that actually costs 200,000 euros. I want to know how well does this model predict every house based on the number of rooms. So how do I do that?
So for that, you can use the root mean squared error, because we talked about how, if I go back to this picture, we talked about the fact that what you're trying to get is that every dot is on the line.
Yes.
If that happens, your root mean squared error is 0.
But it only happens in a perfectly linear
Only happens
world.
in a perfect world. And what we're calculating is the distance from the line, so the predicted value, to the actual value.
Right, because the further that distance, then you can basically say, okay, if I have a lot of dots that have a large distance, that's bad, and if many dots are very close, that's good.
Yes. So we just do that by, calculating the distance using a square and a root, and we use squared and we use root, so it's called the root mean squared error. And if we do that, then we know the absolute distances. But the thing is, if we use a different feature, the scale might be different.
Right.
And then the root mean squared error will be totally different depending on it. If it works better, the root mean squared error can still be bigger because it's all just on a bigger scale.
Right. So we need some way of actually translating the value we found into a comparable value for all different models.
Yes. So we can do that by using the coefficient of determination. And what we do here is we take the explained variation, which is often the mean or something like that, and we divide that by the total variation, which is, basically our root mean squared error. And if you do that, you can see that they give different values, and the root mean squared error is always positive, and the r squared, which is the coefficient of determination, we call it r squared, that one can be negative. If it doesn't make sense at all, your algorithm doesn't really know what to do, it's going to be negative, and if it works better, it's going to be a higher number. So in this case, it's around 0.5. And
so is that good, or is that meh?
I mean, it works better than just random guessing, which is always good. And here you can see that we can plot the predicted values in orange and the actual values in blue.
Yeah. So you had a lot of possible variables, right? You could. We had number of rooms, and we had some others. 15 in total. I mean, I can't imagine a graph with 15 dimensions. So one of these features has to be the best predictor of housing price.
Yeah. So what I did is I just made a little for loop, and for every feature that we have, I am plotting what it looks like the predicted values and the actual values, And I'm also plotting the root mean squared error and the R2 value. So you can see that if you look at the criminality, then the root mean squared error is 8, and the R2 value is way lower. So with the amount of rooms, our root mean squared error was 6, right. So not too different from 8, but we had a way higher R2 score. So that's why R2 scores are so important.
Because you can't directly compare.
Yes, and we can see that we have a few R2 scores that are really low. This one is actually negative, which means that it just doesn't work. It's not giving you any information.
Any idea which feature that was?
That is the Charles River dummy variables. But the thing is, it's a 0 or a 1. So
that's actually a category, so that's not really going to work with linear regression.
Yeah, so you'd have to use logistic regression, for example, to make that work. And we have a lot of different ones, and you can see that the amount of rooms works pretty well, and a lot of other things, they don't work for this algorithm, but they might work very well for another algorithm. So I think this very much shows you that it doesn't just differ like which feature you have, but every algorithm, like every feature might work better with one algorithm or another. And here I only showed it for one feature, but you can build the same algorithm to work for multiple features. But this is just easiest because you can plot everything and it makes more sense in your head. But what we're now doing in 2 dimensions, you can also do in 3 dimensions and just in a lot of dimensions. So
just not in your head, because that's impossible.
Well, maybe in my head. But,
that's good. That's good. Then I'll let you work on that. So this was the algorithm linear regression. You've created one, and now we have the ability to let a program predict housing prices.
Yes.
So after this, I'm very interested to see whether I overpaid for my house. But for now, I think we've basically discussed what we wanted.
Yes.
Except for one important thing, and that is our book recommendation for today.
Yes, we already talked about it a bit. And I have chosen as a book Artificial Intelligence, A Modern Approach by Stuart Russell and Peter Norvig. This one was actually free on their site, and this book is actually more than 1,000 pages, and we used it at university, and it's a really good book, and it goes really in depth, but it also it tries to kind of start at the start, and which makes it easier to understand and follow along. And I mean, it's not a basic book, but if you're really interested and want to know more, especially about how the algorithms actually work, this is a really good book.
Yeah, because what I found, at least up until now, is that you kind of really need to know what your colleagues who are, for instance, more into the algorithm part than you are, what they're actually doing. You need to understand what challenges they face, so that if, for instance, I as a developer have to work together with you, I can actually speak the same language, which would really help. So I'll be taking a look at that book. Thank you very much. And for now, thank you so much for watching. And I hope to see you soon. Bye-bye.
Bye.